Okay, so here, as promised, is the Intermolecular Forces and Solubility lecture. We've talked about a lot of these things already with the demos and things, but I wanted to just make sure there was a place that you could go if you wanted more formal information. So, some terminology. Intermolecular forces occur between molecules, from one molecule to another, just like interstates, like I-5 is between many states. Intramolecular forces hold atoms together in a molecule, so that would be like a covalent bond, essentially. Intermolecular forces, on the whole, are much, much weaker than a bond, an actual covalent bond. You can see it takes just 41 kilojoules to vaporize a mole of water, which is still a lot as intermolecular forces go. Whereas if you were to break all of the hydrogen-oxygen bonds in a mole of water, it'd be 930 kilojoules. So you can see it's a significantly higher amount. So covalent bonds are much, much stronger. But today, we're just going to be looking at the variety of different types of intermolecular forces. So just keep those two words straight. You can see here some of the things that can give us information about a chemical's type of intermolecular forces, different ways you can measure them. You will notice a lot of these things we talk about when it's related to water, of course, because water is the most common chemical that really most of us come in contact with. So we'll talk about a few of those as well. So there are basically 4 types of intermolecular forces, and all chemicals can be sort of divided amongst those 4. You can see number 1 is the strongest, 4 is the weakest. We don't talk a whole lot about number 1, this ion dipole force, even though it's something we do come in contact with. It's basically when you have an ion, so some sort of ionic compound dissolved in a polar molecule, usually water. And because an ion is a full charge rather than just a partial charge, it's just a little bit stronger. The next strongest are hydrogen bonds. So these are polar molecules attracting to one another. But to be a hydrogen bond, it's a super strong kind of the next one, dipole-dipole. Super strong dipole-dipole. You have to have hydrogen bonded to F, O, or N. So hydrogen wants to have FON. Next, we have just our regular polar type molecules, polar to polar. We call those dipole-dipole forces. And I know it sounds silly to say dipole twice, but you're talking about the dipole from this molecule being attracted to the dipole from this other molecule. So that's why it's the force so nice they named it twice. The last one are called London dispersion forces. Those occur in nonpolar chemicals. They also occur in these others. You'll see when we talk about what they look like. But in nonpolar substances, they're the most prevalent intermolecular force. So for our purposes, nonpolar is London dispersion. So we're going to talk about kind of what each of these look like in turn right now. So ion dipole, said we don't talk about it as an intermolecular force very often, but it is something that you experience a lot. What happens is that the cation is attracted to the negative side of a dipole. Let's say this was like HF. So the cation portion would be attracted to the fluorine side, and the anion portion would be attracted to the hydrogen side. And since this is a full charge as opposed to just our little squiggly partial charge, it's just a little bit stronger. It can just attract a little bit more. So next one that I imagine are all familiar with is the hydrogen bond. Remember, it is not a bond, it's an attraction. It's a special dipole-dipole interaction. So it's a super strong dipole because hydrogen is very small and it's bonding with F, O, or N, and because those are all very electronegative, you end up with a very polar molecule. So here are the three most common sort of chemicals, and you can see that all of them can make hydrogen bonds to each other. So here we have water to water. The O is attracted to the H. Here we have ammonia, NH3. The N is attracted to the H. And so, since these both have hydrogen bonds, water and ammonia can be attracted to each other. The third one is hydrofluoric acid, HF. And in that one, it can do a similar thing. It can be attracted to the H here. So, since hydrogen bonds are just a special dipole-dipole interaction, they can interact with any of those other dipoles as well. It just won't be quite as strong. So, here's a little picture. So here you have, of course, water. And this is something called formic acid, which is COH and then O and an H. So you can see right here, you do have a little bit of a hydrogen bond situation. So the hydrogen's kind of positive, oxygen's kind of negative, so you get an attraction. On this side, we have our O, but there's not an H bonded to it. So this O, you can tell that it's kind of negative. There's a lot of electrons there, but it's not going to be as attracted as it would be here because this O is not hydrogen bonding at all. And there you can see our little NO and F, the most electronegative things. So, the hydrogen bond is a special dipole-dipole interaction because it is so strong. If you notice here, we have a graph of boiling points of various chemicals. And in general, the trend that you see is that the smaller the molecule, smaller the mass, the more easily it will boil. So the lower the boiling point. So you can see CH4 is less massive than SiH4 is less massive than GeH4 is less massive than tin. And these are all in a group. So you're just seeing as you go down the group, boiling point is increasing. And we see that fairly consistently in each group. Even, I know it crosses here, but you still see HBr is a little bit harder to boil than HCl and so on. But if you notice, these three chemicals, which all have hydrogen bonds, don't follow that trend at all. They stick together more tightly than any of these other chemicals, and therefore it takes a lot more energy to get them to boil than we would expect for their mass. So, yeah, so those bonds are holding them very, very strongly. Even though something like HCl or H2S, those are both polar. They just don't have that super special hydrogen attraction. They're just not quite as strong. So here is what's happening in those other polar molecules. It's what we call a dipole-dipole force or dipole-dipole interaction. I know, it's silly to say dipole-dipole, but what they mean really is that this is a dipole because it has two poles, a plus and a minus. And this is a dipole because it has two poles, a plus and a minus. And these two dipoles are attracted to each other. That's why it has a silly name. So it is an attractive force, again, between the positive and the negative. But because the electronegativity differences aren't as extreme, you get not quite as much polarity and therefore not quite as strong of an attraction. So here's another picture. This is with HCl. You can see that H, the positive side, is attracted to those free electrons on the chlorine. And so you get right there your dipole attraction. And if this kept going, we could have an H here, and a Cl here, Cl here, and it would create sort of a network throughout the whole beaker, let's say. The final type of intermolecular forces are called London dispersion forces. And these can occur in any chemical, but we tend to talk about them in the context of nonpolar chemicals because that's the only thing that nonpolar chemicals have. So it's a very weak intermolecular force, and it's caused by sort of temporary imbalances that occur just by happenstance, by the nature of the fact that electrons move around. So here we have helium. So you can imagine liquid helium, perhaps. And as helium is just hanging out, just because electrons are moving, there will be times when these electrons are just kind of over here. And so the positive charge from the nucleus kind of pulls on these electrons over here and then leaves this side kind of positive, and then that can pull on the electrons over here. So you're getting a little bit of polarity just for a moment when the electrons line up just so. So it happens, but it's very fleeting. And then it goes back to just being all evenly distributed. So it's really like this is happening at just one instant in time, just a snapshot, whereas hydrogen bonds and dipole-dipole interactions are occurring all the time. They might be moving and changing and switching, but you're always having that polarity, that positive to negative attraction. So, with these London dispersion forces, we can talk about something called polarizability, which we won't talk about very much, to be honest. And that just has to do with how easy it is to get that moment of dipole, that moment of a little more positive here and a little more negative here. Generally, it's easier to have that little moment of a polar state with more electrons and with a more diffuse or a more spread out electron cloud. Dispersion forces increase with molar mass, so that was similar to what we talked about a moment ago. You can see when there's more molar mass, there's more electrons. The cloud is bigger, so it's more spread out, so that kind of makes sense. You can see here there's CH4, CF4, CCl4, CBr4, and CI4. So these are all in a column. Obviously CH4 isn't in the same column, but you can see there's a very clear trend where melting point increases with mass, which is because things that are more massive get held together a little bit more tightly. They're a little harder to separate. So, if we look here, just a few examples of different types of molecules and why, what they have and why. So HBr, it does have a hydrogen, but remember, hydrogen bonding only works with Pon. So Br is not Pon. So it's polar, therefore it has dipole-dipole interactions. There are dispersion forces, which we talked about. At this stage in your chemistry life, it's not important to me that you remember that. CH4 is nonpolar. It's not a very good picture, but that's okay. So it's nonpolar, so the only thing holding it together is dispersion forces. Would CH4 be able to mix with HBr? No, because HBr is polar, CH4 is not. Good job. SO2, this would be a nice one to draw some resonance structures for. It is a polar molecule, so it has dipole-dipole forces. So, the key thing with all of this, and this is something that you know it in the context of water, and you know it very well. Just when we start to add other chemicals in, you might doubt yourself. Don't do that. The way a substance behaves macroscopically is entirely dependent on its intermolecular forces. And what determines those, what it's made of, and its shape. So, intermolecular forces for the win. So these now are just awesome examples of things that we see in light of various intermolecular forces. In particular, of course, related to water, because water has very high intermolecular forces. So one thing we see is a high surface tension. So the stronger the intermolecular forces, the higher the surface tension. And that's because each little molecule is being attracted to all the ones around it. Something pretty interesting happens when you get up to the boundary. All that same force, all the same attractions are all just being sort of sent downward, and so you get a very, very strong layer up at the top. Now, imagine, if you will, that we had, let's say, NH3 in the speaker. Would it have a high surface tension? Well, then you have to ask yourself, what kind of intermolecular forces does it have? NH3, we have an H bonded to an N, so it's hydrogen bonding. So that, therefore, is high surface tension. So even though ammonia is not really something we come in contact with a lot, which is good, because it's really volatile and smelly, it would behave in some slightly similar ways to water. Adhesion and cohesion, again, you've seen this a lot, in particular with water, of course. You talked about it in biology. This is how trees drink. Cohesion is the intermolecular attraction between like molecules. It's like water to water. Or mercury to mercury. Whereas adhesion is an attraction between unlike molecules. So that would be, in this case, the water is attracting to the glass molecules, both of which are polar. The water will adhere, will stick to other things that are polar, which is what we see here. But it will also stick to itself because itself is polar. Viscosity is a resistance to flow. If you've ever had pancakes or waffles or French toast with syrup, you've perhaps seen a viscous liquid, kind of thick. And if you heat up the syrup, the viscosity decreases. It gets less thick. In general, things with strong intermolecular forces of similar masses, the stronger the intermolecular force, the more viscous. As you get to more large molecules, bigger molecules, they can start to sort of tangle together, and then they can become more viscous in that way, without necessarily having stronger intermolecular forces. So, and finally, this we talked about on Friday during the demos. You can see water is very unique because of the way that it freezes, that it becomes a solid. Most things just sort of pack together when they form a solid. Like packed together like that. Whereas water makes these very specific structures. And so you end up with these big holes inside of your ice, which sort of pushes it outward, makes it take up more volume, and you get a less dense structure. So that's very unusual, but it's explained entirely due to the intermolecular forces. Because water is so tightly bonded to itself, when it freezes, it has to be aligned so that the positive hydrogens are aligned with a negative oxygen. So, excuse me. That's just sort of a brief overview of intermolecular forces. It's important to remember the stronger the intermolecular forces, the harder it's going to be for things to boil, to evaporate, to heat up in general. They might have higher surface tension, and all of those things come from intermolecular forces. The other thing that you're investigating in your lab has to do with solubility. So things that have similar intermolecular forces, hydrogen bonds and dipoles, will be soluble in one another, whereas things without similar intermolecular forces, so water and oil, for instance, hydrogen bonds and London dispersion forces, they won't mix because they can't interact with one another. So, thank you and goodbye.